Everybody's ready? All right. Cool. Okay, so that was a lot, right? But you can see the power of this tool, right? It's like creates some really interesting interactive graphics, and there's a lot of there's a lot of tricks that we didn't really talk about because I just wanted to give you the basic template. But imagine all the degrees of freedom that you have in generating interesting graphics. You can arrange the masks in more complex ways, right? So I showed you pretty simple ways like linear interpolation, circles, rectangles, but you can imagine doing masks that are much more complicated. Maybe they're shaped like tessellations. That's one that I've been wanting to do. I just haven't gotten around to it. So maybe somebody else will instead. Or you can use images as sources and then segment the images, and you just get much more complicated shapes. Another thing is changing the actual channels that you visualize. That also makes a big difference. And if you're making video, then the way that you distort the canvas also makes a difference as well. Because you can, for example, you can distort the canvas using the zoom in technique, or maybe you can do something like shifting, translating, or maybe you can deform it using something like Perlin noise or sine waves, or things of that sort. So there's all sorts of ways of extending this technique to get more interesting results. So that's something that that you may wish to play with a little bit. And actually, recently, the team behind Distill.pub, which is this nice little publication about trying to understand machine learning, they've made a successor to Deep Dream that they call Lucid, which is extending the technique even further. So that's something they have a blog post about that you can read about. But we're going to kind of move on. So what the rest of today is going to be, I'm just going to give you a lecture about generative models. This should be pretty fun. I'm going to show you a lot of recent work in this field. And I'm going to actually show a few things that will be relevant to us tomorrow, because tomorrow I'm going to do a demonstration of a bunch of well, we'll see how many we can get through, probably a couple. I'll try to focus on the ones that are easy enough to adopt. But I'm going to show you different classes of generative models, and yeah, some of the cool things that have been coming out in this space over the last couple of years. And I'm going to kind of nest this lecture inside of an explanation of what generative models are. And for that, we're going to kind of then I'll show you kind of pix-to-pix stuff. So yeah, one of the thing that we'll probably end today with is going to be an explanation of pix-to-pix, which I showed you I've already shown you a couple of times, right? So the Trump face thing that I did, as well as a handful of other projects that I'll show you later today, are using this technique called pix-to-pix. And pix-to-pix is a type of generative model which I'm going to basically lead up to. So the whole purpose of this lecture is to try to go from scratch to understanding how pix-to-pix works. And we're going to take very broad sweeps. It's going to be not exactly the most low level, the most granular explanation, because that would take a PhD to do. But it will be enough so that you can kind of understand, at least have an intuition about what these things are or how they work, right? So what are generative models? This is kind of something that you might hear about. If you're reading the research, you'll hear a lot of people talking about generative models. And generative model is actually a term from statistics. It's basically any model of a data set which tells us the probability of any possible point in that data set. In other words, let's say you have a data set of images, and all of those images are of faces. Then you can think of an image as being a combination of pixels, right? And in your data set, you have several of these combinations of pixels, right? You have many. Let's say you have 100 of them, or 1,000 of them, or 10,000 of them. But really, in your data set, you have many possible images, right? If your images are 100 by 100 pixels, you have the space of possible images you can make with that is at least this many, 30,000 dimensions, right? So within the scope of 30,000 numbers, you can make many different kinds of images. However, most of them are not very likely to occur, right? Most of them are complete garbage, right? They're nonsense. They're just noise. Most images, most possible images, are noise. And so a generative model tells us what images are actually realistic, right? It tells us which images are probable or likely to occur. Actually, I'll have this in a few slides. This will make a little bit more sense. So I'm going to explain the simplest kind of possible generative model, and it's something called principal component analysis. So how many people here have heard of principal component analysis? Okay, so maybe half of you. So principal component analysis is something that you would learn about in say an introductory statistics course. It's generally a way of reducing the dimensionality of data, but it turns out that it can be a nice generative model as well. So let me very quickly give you the top level view of what principal component analysis is, and then we'll see what you can use it for. I'm going to show you some like fun projects. So first of all, like principal component analysis starts with the following observation. Let's say you have a data set of something. Let's say this is a data set of points, and these points are houses, something like that, right? Each one of these points refers to a house. And the x-axis refers to the size of the house, and the y-axis refers to the price of the house, right? So size and price. So intuitively, you'll think, well, size and price are correlated with each other. Big houses are more expensive, right? So if you plot those houses according to size and price, you might find that they look something like this. You can see that there's a positive correlation, that as the size gets bigger, so does the price. It's not perfect, but it's something like that, right? So PCA says, principal component analysis, says maybe we can take this data set of houses and find a new representation of it, which has just one number instead of two numbers. Maybe some sort of a combined statistic that captures both the size and the price of the house in one dimension. And the way that you can do that is by finding a set of vectors in this data set, which are orthogonal to each other, they're perpendicular, that we can use to rotate the data into a sort of new set of axes, and then basically get rid of one of the axes, get rid of the short axis. So here you see we find this like vector that runs through the dimension of the data which captures the most variance, right? The most variance of the points lies along this vector. And so then we take that data set and we rotate it so this becomes our new x-axis. And then imagine that we took all of these points and we just projected them down onto this line. We flattened it. So we take this cloud of points and I were to just flatten it together by projecting all the points down. Then what you would have is a new data set which lies along one dimension instead of two, and all of the houses are now just a point along this line. Now, that may not seem very useful, but it's useful for a couple of reasons. We have made the data set smaller, has one dimension instead of two, and we've also made it kind of denser. So in other words, like we have all this empty space here. It's not useful for anything. We can get rid of the empty space by projecting the data set down into one dimension, which is actually very densely sampled, right? So you can use this to find representations of data which are lower dimensional. And this is kind of useful for many reasons, but one of the reasons we're going to actually come to. So imagine instead of doing this in 2D to 1D, we can do it from 3D to 2D. So imagine now you have a new data set, and it's in 3D. And you have a whole bunch of points. Now don't worry about the labels, like you see pink, blue, green, and red. Imagine they're all, this image comes from Wikipedia, so, or from, actually, no, it comes from somewhere else, but it's just an image I stole. Imagine you have all these points, and all of the points, although we represent them in 3D, if you look at them, they seem like they actually lie very close to a plane that cuts through the space. So you have like a three-dimensional space, but really all the points appear to be very close to this plane that we can see here. So imagine we found that plane and we took it out. We like just grabbed it out of the original data space and we used it as our new representation for the data. And then the thing is that all these points, they don't actually lie on the plane. They lie very close to it. We find the plane that lies close enough to all the points that we can project all of the points, even though they're not exactly on the plane, we can project them down onto it and then have this new representation. These are what are called principal components, right? And the thing is that we have found a new representation for the data that has 2 points instead of 3, but it has a few properties that are nice. The properties that are nice is that we've gotten rid of all of this empty space. It's gone now. And so now we have a new representation which is densely sampled with actual points from our data set. So it's smaller and it's more compact and it's more dense. However, there is a flaw. We have actually corrupted the data set, right? Because all of the points, because they're not exactly on the plane, we have to project them onto the plane, and that means they shift a little bit, just a little bit, right? And so this means that we are corrupting the data. So you could actually reverse this process. You could say, okay, if you save the transformation that you did, that you remember how to go from this to this, you could always go back into the original data space, right? However, if you go back, having corrupted these points, having projected them into the plane, then when you go back, the points won't be exactly where they were in the first place. They will have shifted a little bit. They'll be on this plane. So this is actually like very similar to compression, right? It is compression, right? So this is in fact a way of doing compression. Now it's a lossy way of doing compression, right? Because you will reconstruct the original data, but it will have been corrupted. All of the points will have shifted a little bit. So PCA is actually a form of compression. Now let's think about this in the context of images, right? Imagine that you have images of size 32 by 32. So here's one possible image, right? And it might look familiar, right? So this image has 32 pixels by 32 pixels, and it's color. So it has 3,072 dimensions, right? 3,072 numbers, right? Now, you can think of all the possible images that have 32 by 32 pixels. You can think of that whole space of images as being like a gigantic 3,072 dimensional space, right? So imagine now, of course, you can't imagine 3,072 dimensions, right? But it turns out that math works exactly the same way in 3,000 dimensions as it does in 3. So just imagine in your head, you can kind of imagine 3 dimensions, but just say 3,000 very loudly. This is a quote by Jeffrey Hinton that I like. So every possible image is like a point in this 3,072 dimensional space. But if we have a data set, and that data set is of, let's say, things like faces, then what we know is that the actual data set is like a bunch of points inside of this 3,072 dimensional space. And so that's kind of, just imagine that for a second, right? Now, so yeah, let's say you have a bunch of these faces. Now here's the thing with PCA, what PCA tells us. All of those possible images, and there are very many of them, this is the number of possible images in 32 by 32 pixel space. So if you have 256 possible pixel values, that's 256 raised to the 32 times 32 times 3. It is a absolutely gigantic number. It's a number that is like hundreds of thousands of digits long. I think it's 170,000 digits long or something like that. So it's incredibly large. The number of atoms in the universe is 80 digits long, and the number of possible 32 by 32 pixel images is 170,000 digits long. So, but here's what we know though. Most of those images are of random noise, right? Just random pixels. And by most, I mean the overwhelming vast majority of possible images inside of 32 by 32 pixels are of junk, random noise. So if you have a data set of faces, you could, for example, try to compress it using PCA. And this would be a good thing to do because it turns out that most possible images are not very likely to occur, right? They're random junk. However, some of those images inside of that 32 by 32 pixel space are likely to occur, right? Like this image right here, right? Well, it actually has a 100% chance of occurring because it actually occurs in our data set. But you can imagine that there are fake images of faces which are likely to occur if we were to do an analysis. Like they are likely to occur given a model of these images. So this is the process, and this is the simplest possible generative model. We get a data set of faces, right? There's several thousand faces called faces in the wild. These are all celebrities, as you can see. Some of them are pretty familiar, right? Mostly politicians and athletes and things like that. So with I'm going to skip this slide. So basically, like the idea of PCA is that you can always do this from any number of dimensions down to any number of other dimensions, right? So let's say we have this data set of faces and it has 3,072 dimensions. We can apply PCA to re-represent that data as having 100 dimensions, let's say, instead, or 500 dimensions, or 1,000 dimensions. And PCA lets us do that. It's this transformation of a large high-dimensional data set into a low-dimensional data set. And it's invertible. So PCA goes from the original set of pixels, 0, 0 red, 0, 0 green, 0, 0 blue, 0, 0, 0, 1 red, 0, 1 green, so on, into a new set of principal components, which is smaller. And the process can be inverted. It's just a reciprocal multiplication. So you can go back from this to this. However, here's the thing. As I said before, remember that if you go back from principal components to the original images, we corrupted the original data. We corrupted it so that when we go back, it won't be exactly the same as it was here. This will not be equal to this exactly. It will have been corrupted by this compression. So let's say we did this process and we took a random image of George W. Bush here, right? And this is the and this is the original image. And then say we did this PCA of all of the images in our data set, of all of the faces, and we transformed it down to 2,000 dimensions. So we have a PCA of 2,000 dimensions, and then we invert the process. We go backwards. We'll take the image of Bush and go back into pixel space. So if we do that from 2,000 PCA dimensions, we get this. And you see that it's a pretty decent reconstruction. It looks a little bit like, you can see like compression artifacts, but it's pretty decent, right? But if we do 1,000 dimensions, still looks pretty decent, right? But now it looks a little bit almost like blurrier. This is from 500 dimensions. This is now from 100, I think it's 100, yeah, 500, 100. Now it looks like it's becoming like we're getting rid of all the details, right? And this is kind of like the idea of PCA is that as you get rid of principal components, you get rid of more and more of the detail. And they're ordered by the thing that captures the most variance in the data set. The most important feature is the first principal component. The second most important feature is the second principal component. The third most important feature is the third principal component, and so on. And so we keep on getting rid of progressively more important features. And so the PCA is forced to learn a representation that captures as much of the diversity of the faces in its data set as it can in as few numbers as possible. And that's, of course, very difficult. It's very lossy. And so it keeps on losing more and more detail until, as we get to it, we can actually represent the PCA as, let's say, 2 numbers or 1 number. And then, so this right here, this image, is actually represented by 2 numbers in our original PCA space. And then when we go back from the PCA to the original pixel space, you get this bland looking, man in a suit and tie, right? And this is just one number. So this is actually kind of impressive, right? Because the original image is 3072 dimensions, but this is just one number that represents the entire thing. So this is like extreme compression, right? Now it turns out to be not a very good way of doing image compression. JPEG is much better, but this is a way of doing image compression. So this happens no matter what face, as you select any face in the data set and you run this process and you progressively take away as many of the columns as possible, all roads lead to, George W. Bush, basically. So, and this is now, why does it look like this and not more like any of these faces? Well, that shows the bias in the data set, right? It has a lot more images of white men in suits and ties than it has of other people. And it has actually 400 images of George W. Bush, I think, so. So that's the most representative sample is George W. Bush. So this is actually a neat way of actually finding but of course all of the images are of faces, so it is going to learn something about faces, right? And you can actually represent the essence of a face inside of just one number, if you wish to, right? Inside of this. So now let's say you have this generative model. And you've compressed, it's a generative model now because we can actually sample from the PCA space. Basically we've taken all these faces, which are, now it's not 3 dimensions, but it's 3072. And we've projected them down into some 3-dimensional or 2-dimensional surface. And if we do that, that surface is going to be very, very densely sampled with faces. It's going to be like the sort of there's a term in mathematics called a manifold, which is like a subspace of a larger space, right? This plane is a 2D manifold inside of this 3D space. So let's say we find some 4 or 5D manifold inside of a 3072 dimensional space, and then we force all of the points to be on it. That means that all of the points are going to be on this very, very small subregion of the original space, which means it's going to be very, very densely sampled. Which means that any possible point on that manifold that we pick, even if it doesn't correspond to an original point, should look similar to its neighbors, right? So this is a very simple generative model because we can just pick points from that space and then reproject them out using PCA and get something that looks like a face. So if we take 2 actual faces and take their PCA points and then draw a line between them, and then at each point interpolating along the line we sample an actual face from it, you see that we'll get something that looks plausibly like a face. And even cooler is that we find a transition between 2 different faces that kind of changes smoothly, reasonably smoothly. And what's even cooler is that you see that it learns high-level features of faces. So for example, you can see that from this point right here to this point, the hair gradually becomes a hat. So that's kind of cool. You see a morphing of hair to hat along some vector in this PCA space, right? And you can actually then just sample any random point from this PCA space, project it out into the original pixel space, and you get things that look plausibly like faces. Now they look pretty blurry and abstract, but you can see faces in there, right? But these are all fake. These do not actually correspond to images in the data set. And you can do interpolations between them as well that show smooth changes of hair color, of skin tone, of even, you can see some faces rotating. You can see them kind of going from looking left a little bit to looking right a little bit, or maybe the brow is changing. This one I see kind of moving around a little bit, right? So this is, now PCA is actually not ever used for this, but it's a it's usually used for dimensionality reduction, but it actually turns out to be like the simplest possible generative model, and a reasonably reasonably understandable if you take like a physics course. So this is, yeah, very nightmarish, right? Now here's the thing about PCA. PCA is fundamentally limited. It's limited because it learns a linear dimensionality reduction, right? It learns it finds a plane or a hyperplane. It's a flat structure. So even if we do this in 100 dimensions, we're getting the 100-dimensional, what's called a hyperplane. A hyperplane is a 100-dimensional, analogous to what a plane is in 2-dimensional space. It's flat. Now, what flat means in 300 dimensions or in 500 dimensions is not, it's not like a piece of paper, but it's basically has the same properties. It doesn't curve, right? Which means it's a little bit limited, because sometimes data is not distributed along flat planes. It's distributed along curves. It's distributed along like more irregularly. So PCA is limited because it's a linear technique. It doesn't actually represent data very effectively. What represents data much more effectively is something called a neural network. A neural network which is not linear. So in the interest of not going too deep into this, I'm going to go through the next few slides like relatively at a high level. I'm not going to talk about how these things work at a very, very deep technical level. I'll just kind of give you the high level overview so that we can get into the applications, which I think will interest people much more. So instead of using PCA, we can use something called an autoencoder. And an autoencoder is a very special type of neural network. Now we've already looked at what basic neural networks are, right? This came from yesterday or 2 days ago, right? We introduced neural networks. Neural network is a structure that takes in some input, goes through a series of multiplications and additions and other mathematical operations until you get some output. And if you train a network, like let's say to do image classification, you can learn a very effective mapping of one kind of data, which is pixels, to another kind of data, which is like a classification. So most of the neural networks, or all of the neural networks that we've looked at so far, are built this way for doing classification. So it takes in some input, and we have some data set that tells us what all of the inputs mean, a label. And then we learn how to predict the label from the input, right? That's the kind of neural networks that we've had so far. But an autoencoder is a special type of neural network which works a little bit differently, right? So this we've seen all this. In an autoencoder, we do something really, really silly. We create a neural network whose output layer is identical to its input layer. It's identical in size, and then there are no labels. There's no categories or classifications or regression. We instead just have input data, just images or sounds or text or whatever. And we train the neural network so that it reconstructs perfectly the input. So the input is trained to be identical to the output. In other words, it's just the world's most expensive times 1, right? So it's basically a neural network that takes in some input, and it goes through 100 million multiplications and additions, and then comes out on the other side exactly the same. So it's the world's most expensive times 1. Now, that may not make a lot of sense. Like when I first heard of this, I was like, why would you do that? It seems kind of wasteful and pointless. But the reason why it's done is that it actually functions in very much similar way to how PCA functions. If this neural network is set up so that somewhere in the middle you have a sort of bottleneck where the number of neurons in one of the middle layers is very small, let's say 3 neurons or something. If you're asking this neural network to reconstruct a very high dimensional input at its output, but you constrain it so that at some point in the middle, the transformation leaves the data as being represented only by 3 numbers, right? Then you're constraining the network in a way that you're asking it to do a lot. You're asking it to go from 3 numbers back out to the original input in such a way that minimizes the error. So think about how hard that is, right? You have, at some point, the image has projected through several layers of multiplications, and you have only 3 numbers. And to get out back in such a way that captures all of the original data, that's really, really hard and unlikely. And the only way that the network can do it is by learning a very efficient representation of the original images. In other words, it needs to figure out, like, okay, if you're only letting me understand the image as 3 numbers at some point, then these 3 numbers better capture like some very, very high level pattern, some very, very high level feature, right? This is kind of like what we do when we look at objects, right? Like if you look at cars, for example, you recognize cars as like a combination of some high level features. You know, maybe one feature says it's a sedan or a truck, or, you know, or some other kind of shape of a car. And another dimension is the color of the car. Another dimension is, you know, the make of the car, or, you know, something like that, right? Here, what ends up happening is that the neural network does something similar. It memorizes like a set of high-level descriptors for the data set that you give it, such that it is able to go from those to the original input very effectively. So this actually, if you abstract, is very similar to PCA. The first half of the neural network is like the encoding part that goes from the original input to some high-level representation of fewer numbers, like your PCA components. And then the second half of the network is the decoder. It goes from the high-level representation back out to the image. So this is very similar to PCA functionally, except it's better than PCA because it's nonlinear, which means that it can fit much more irregularly shaped data. Something like that. That's the sort of high-level overview. So for example, if you did this with digits of images, it can reconstruct them effectively, although you see that they come out kind of blurred, right? And that's kind of the compression artifact. They come out sort of looking a little blurred, and in some cases it even changes the digits. Like this thing right here, it looks to me kind of like a 5, right? Or maybe it looks like a 3, but because it's a very unusual type of 5 or unusual type of 3, it sort of ends up getting corrected to something that looks more average. And yeah, it ends up looking like more like a 3. And so it makes mistakes, but it captures the essence of these numbers, right? Now and if you're already confused, this will confuse you even more. But don't worry, because you don't need to understand the internals of this. I don't fully understand the internals of this either. So, and I don't know if anyone really does. It's like because the thing that the thing that I'm about to tell you about was invented in 2014. So like nobody in the world, you know, think of the smartest person in the world that you know, like they couldn't have understood this before 2014. So this is super cutting edge, like, and it's a really cool idea. So basically, and it was come up by one person. So if you ever heard the name Ian Goodfellow, if you've been tracking the machine learning space, this guy Ian Goodfellow came up with this idea that that is now being used for like a ton of stuff in machine learning, and it's called a generative adversarial network. So how many people here have heard of generative adversarial networks? A handful of people. So generative adversarial networks are basically the following. So it's kind of like an autoencoder in the sense that it's a generative model that's using a neural network. However, instead of using a neural network, it uses 2 neural networks. It has 2 neural networks now instead of 1. It has what's called a generator and what's called a discriminator. So G and D. So you can think of G as being kind of equivalent to the decoder in an autoencoder, right? And you can think of D as being equivalent to the encoder, except they've been split up in the following way. So this is what the generative adversarial network is trained to do. The generator is it's a neural network whose input is basically a random number. So it's like this random number Z, or it's not just a random number, it's a random vector. And it produces an image. So you get this random number and it produces an image. And the generator, its goal is to synthesize images which look like they came from the original data. So synthesize image, so take at its input a random number and poof, on the output, create an image that looks like a real image, right? And D, the discriminator, its goal is to tell whether or not the image that it's receiving is from the original data set or is from the generator. So the analogy is, so D is saying this is real or fake. So the analogy is that G is like a, like a counterfeiter. So G is trying to create counterfeit paintings. And D is like a police officer. It's trying to say whether the paintings are real or fake. And real means that it came from the original data, and fake means that it came from the generator. So what happens is that these networks are being trained at the same time. G is being trained in order to try to fool D. And D is being trained in order to try to tell whether or not it's like trying to figure out whether or not the image it's receiving from G is real or fake. So they're competing, right? They're kind of locked in this competitive battle, and they're being trained at the same time. And in the beginning, both are very bad at what they do, but they're locked in this sort of arms race, and they're being trained at the same time. So G gets better and better and better at fooling D, and D gets better and better and better at telling apart G from the real data set. That's why it's called adversarial, right? So they're competitive with each other. And what happens is that after this arms race, they both become increasingly really, really good at doing what they're doing. And in particular, G is really, really good at generating images that look real, better than autoencoder, in fact. Yeah.
This assumes that D was not trained on the full data set, right?
So D is trained on images coming from X, the data set, and coming from G, right? So that's basically.
But it can't be the full data set, right? Because then we'll just be able to memorize those images.
Well, so it can't necessarily So if we made it, if we trained it in such a way, so that's actually a danger. If D was to memorize the data set, then it wouldn't generalize very well. So it wouldn't. Then it wouldn't be very good at doing this. So basically, what would end up happening is that it would underfit. So if it memorized the whole data set, the whole process is overfitting. So it's not very good.
But actually, if it memorized the data set, it would know right away if anything was coming from the data set or not.
Yeah, but it can't memorize the data set because it's not big enough. It's like it doesn't have the capacity necessarily to do that. And if it did, that would be bad news for us, because we need it to generalize to possibly unknown samples. Because then G would be no good. Like it wouldn't work. So in 2015, a paper came out called Deep Convolutional Generative Adversarial Networks, DCGAN. And basically, this was the first attempt at having convolutional layers inside of GANs. And they were able to show making realistic looking faces. So all of these faces are totally fake. And they're generated by the generator. Some of them are really weird, right? But this was the first attempt at doing this. And before people, so the thing that I showed you earlier, this is something called Eigenfaces. It's actually it's a technique that dates back to the 80s or 90s or something like that. Like running PCA and images of faces. And you can see that these faces are not terribly convincing. They're really blurry and, but we've been able to do this for a couple of decades, on some level, just not very, very well. When we figured out how to train autoencoders effectively, we got much better at it, but they were still kind of blurry, and I don't have the samples here. But basically, let's say better than what we just saw, but not as good as these, right? Because these are very crisp, and they look like humans. Uncannily, right? something like humans. Now here's the cool thing, and this paper is really, really wild, and it kind of started the GAN craze, so I would recommend looking at it. You can find it online. So they talked about like the nature of this generation process, right? So like, remember I showed you in this architecture, I said, okay, G gets trained on some random vector Z, right? Some random number goes in and poof, you get out an image, right? But here's the whole point is that Z, it can't be quite random, right? It has to be able to capture all of the sort of high-level properties of the face in exactly the same ways that autoencoders do it. Oops. You know, an autoencoder and PCA and generative adversarial networks, they have this bottleneck, right? And we often call this bottleneck Z, right, as a shorthand. And sometimes you'll hear it called a latent space or a latent vector. And basically, because we constrain the network to representing all of these points as small bit vectors like Z, it has to learn, in order to do a good job, it has to find high-level features and assign them to sort of vectors inside of this latent space. And so, which means that if you vary Z slightly, then you vary the output slightly. So you have this sort of smooth space of faces or something, right? And they showed that if you can do arithmetic on them, right? So basically, here's the idea. Suppose you found the vector Z, which produced images that look like faces of a smiling woman, right? So this is your smiling woman. And then you found the vector that generates faces of neutral woman. And neutral woman just means a non-smiling woman, right? And then you added the Z vector for neutral man. So you got smiling woman minus neutral woman plus neutral man equals smiling man, right? Because basically woman minus woman, so woman cancels out. Smiling minus neutral plus neutral. So negative neutral plus neutral. The neutral cancels out. You're left with smiling man. So woman minus woman and negative neutral plus neutral. So you get smiling man. So you can do arithmetic on this generative space. So they also have, like, for example, I think glasses. Yeah. So man with glasses minus man plus woman equals woman with glasses, right? So that's pretty neat, right? And they showed these interpolations that you can do. So this space Z becomes very, very smooth. It's very smooth because, again, small changes in the latent vector produce small changes in the output image. And they put out this video of crazy faces, right? Now this is actually from 2015. And we've actually come a really long way. You'll see a few slides later that show just how far we've come with this process. So, okay, let's show what you can do with this, right? So first of all, you can train it on, let's say I gave it the MNIST data set, which is of all of our handwritten digits. So it learns this representation of the images for which is also conditioned on the labels. So we've talked about just sending images, unlabeled images, but you can also provide the labels with it. So that's like a conditional DC GAN. So here we have a label, and so we can generate 4s, and we can generate 9s, and we can generate 6s. And then if we vary, we can actually interpolate between the class labels. So I can say, okay, produce me a 1, produce me a 5, or produce me an image which is half 4 and half 5. So it's like the average of 4 and 5. And I don't mean 4.5. I mean like a character that looks halfway between a 4 and a 5. Or halfway between a 9 and a 7. Or halfway between a 6 and a 3. Right? And here it's just counting up. But you see that like every intermediary step looks like it came from the original data. Right? Or it looks like it could convincingly be a character, except that's not real, right? Because there's no character for halfway between 4 and 5. But nevertheless, you get these very smooth interpolations, right? So the first project that I did with this was actually on handwritten Chinese characters. So I found this data set called HITOR3C. You can look this up. This is a gigantic data set collected at Harbin University where they basically had people in mainland China just, write simplified characters. These are, sorry? What was that? It's a copy? Oh, okay, sorry. Well, anyhow, you can see that these are actual handwritten samples from people, right, of different characters, and there's I think over 1 million of them, and they were collected actually not for what I'm about to show you that I did with them, but actually they were collected for optical character recognition. So you're training a neural network to basically tell you which character it's reading, right? So that I can have my phone app that lets me look at a Chinese menu and it translates it to English for me, right? Because it has to be able to identify the characters. So that's what this data set is for. So I had a different idea, and I got the data set from them, and I basically ran DC-GAN on them. I'm going to show you the results. I think I showed this briefly on the first day, right? So I'm going to go through this briefly again. Basically, you can see now you understand the process. Well, to the extent, I don't even understand it really, but to some degree, you understand where this comes from. It comes from a DC-GAN. So a DC-GAN was given all these images of Chinese characters, and it learned to synthesize images which look like they are of Chinese characters. So these are pairs, and the ones on the left are real, and the ones on the right are fake. And you can see that it does a kind of decent job, right? Maybe it starts to, the more complicated the character, or the more rare the character especially, the worse it gets. So that's kind of falling apart at that point, right? But they're kind of readable mostly, right? Reasonably. So
by fake and real, you mean in the data set or generated?
Well, actually, yeah, exactly, yeah. So left is in the data set and right is generated by the generator. So you can do these experiments where, okay, for here, you take that latent vector z and you sort of modulate it. You maybe do a little loop. So I'll take two endpoints, two random vectors z, and I'll kind of loop between them. And at each point, I'll generate one character. And as you modulate z gradually, you gradually change the character. And you change it along dimensions by which it actually varies, right? Because it's trained on the actual handwritten samples. And so it has to learn these features. It learns that some people write wider, and some people write more narrow. And some people make loops like this, and some people make loops like this. And there's a lot of diversity, right? People have all sorts of different handwriting styles. I imagine it's nightmarish, learning people's handwriting styles, because it's hard enough when there's only 26 characters, right? But when there's 5,000 of them, right? It's how can you read each other's writing? I imagine it's very difficult. But these, it's supposed to try to capture the sort of ways that they vary. And you can see that each of these points looks compellingly like one of the characters, right? And furthermore, you can do interpolations between characters, right? So there's a bunch of them. And you see that it finds very smooth interpolations between characters, each of which are, each of which look almost like they came from the data set. And actually, I don't think I showed this the other day, but I did these experiments where I would try to do a set of characters that had the same radical, right? There's 214 radicals, right? Like the person radical, radical 9, right? And what I found was in some of them, at least I cherry picked the ones that worked, but in some of them, the radical would be kind of preserved during the interpolations. So here, I've highlighted it in red, and it mostly you see the radical kind of shifting around and always staying in place. It doesn't always work. It actually sometimes doesn't work very well at all. But I've cherry-picked examples that do work. And then this is actually this is really stretching it. So this whole man minus woman with glasses plus man with glasses, so stuff like this. So I tried to okay, so if you take the vector which produces king and subtract male and add female, then you should get the vector for queen, right? This is like the word vector trick. So obviously that's not the character for queen, but it could be, right? Like who knows? And like if you think of characters arithmetically, then maybe they could. Maybe that's like an accident of history that it didn't turn out that way. Now other people did this with other images. So these are like DCGAN flowers, manga characters. So these are all fake manga, and you can do interpolations of them. And then I had a student in one workshop who trained a DCGAN to produce images that he trained the DCGAN on the data set that he collected of photographs from Instagram which had 0 likes. So basically he just scraped Instagram and downloaded a whole bunch of images which have no likes in them, and then he trained the DCGAN to produce them, and then he made a Twitter bot that would post these random images, and not only that, but they would also then have another neural network which was trained to caption images to give them captions. So you would generate this image, and then another neural network would try to tell you what it is. So this is man takes a picture of himself. Like it reminds me of those. I always forget what they're called. Rorschach diagrams. What are those things like you take a psychology test where they Rorschach diagrams, right? So it's like, this is a man takes a picture of himself. It's very abstract, but you can kind of see, like, I see a camera right there. It's like kind of like taking a selfie, right? Here's another one. This is dog looks at a cat in the mirror, which is really, really bizarre, isn't it? Like a dog looks at a cat in the mirror, and if you look at it hard enough, you can see it. I see the dog right here, and there's kind of a cat face there, right? Dog looks at a cat in the mirror. And I also like how it memorized the cheesy Instagram filters. See the border thing happening here? So this is just other stuff like in the research, like, okay, so GANs can be used for all sorts of things. I'm going to show you some applications of GANs. GANs can be used to try to predict the next frame of a video. So let's say you have a video and you have 10 frames, and it's like, can you use a GAN to generate the next few frames of the video? And it's pretty crazy, like, and really, really frightening, especially the babies. It's like, so these are all video predictions. Yeah, it's very poetic too, in some way. DGN. Okay, so this is now. Okay, so now all of that I showed you was from basically like from 2015. So these have gotten a lot better since 2015. So I'm going to show you like more recently how good they're getting. So these are what are called deep generator networks. I don't have time to explain too well how these work, but it's almost like a combination of DCGAN and Deep Dream a little bit, like internally. So these are images of cheeseburgers and swimming trunks and barns, leaf beetles, candles, table lamp, sandbar, French loaf, lemon. See how like they're starting to look uncanny, right? Like very realistic. Okay, so like for example, I think I have a few. Oh yeah, this is a visualization of all these classes: tiger sharks, electric rays, stingrays, hammerheads. This is all software that's online, by the way. You can use the software. So I generated these with the software that they released. Starfish, crayfish, puffer. Yes, yeah, so they come from a labeled data set. Yeah, they have to be trained in a labeled data set if you want the labels. Hamster, guinea pig. These are cute, huh? It's like... so yeah, if it's overfitting, then you know you have a problem. Then you're not going to get a lot of different kinds of guinea pigs, right? So that's overfitting is a constant like nemesis in machine learning. They're always trying to figure out how to not overfit. Yeah.
But if you try it like this, do you get decent variation between these things?
If you get what?
Oh, you said you generated these from this program.
Yeah. Oh, so I trained it from it's from a pre-trained data set already. So like these are just like using a pre-trained, because I don't have a data set of like 14 million images in my computer. So okay, so yeah, well I haven't described how DGNs work exactly, but DGNs are like I said, they're like a little bit like a combination of a DC-GAN and Deep Dream. So it's trying to train the generative model such that it produces an image which maximally activates a particular neuron in a neural network. So the process of finding let's say you want to produce an image of this is a macaw. I think this is an actual macaw. So it has this generative model trained over all the images, and then you have to find the right input code which will maximally activate the macaw classification and 0 for everything else. And so they use gradient descent actually to figure it out, and this is the process of it actually finding the right code. So it's like searching through this space, this generative space, until it finds the input vector which will generate a macaw. Right. Takes a little while. I put it on speed. I have the next few in speed dial. And then finally it gets into some bird territory, and then it finds a macaw. Right? This on the left is a teapot, and one on the right is a cheeseburger. I just take a few screenshots of like images that I liked. So the cool thing is it's not trained on people per se, but it's trained on a lot of things that have images of people in them. And so it learns these weird abstract representations of people. So this is a conference center and a nursing home and a lecture room. I guess that's what I look like, right? Several people have said that before. Yeah, Francis Bacon-y. Yeah. This looks like a certain president. I won't tell you which one I think it is. Oh yeah, maybe yeah. So here, I really like this one. This is of boathouses, and what's really interesting about this, if you look at it, the generator learned reflections. Like you see that all of these, it has water, and the water appears to have reflections of the houses. That's pretty cool because like doesn't have explicit knowledge of that. It actually learns that as a feature. And but what's really spooky though is if you look at some of them, sometimes the reflection doesn't actually like match what's inside of the image. It's like a reflection of something else, so it forgot at some point. It's kind of spooky, right? It's like a little bit like a horror movie where the reflection is different than the actual thing. Okay, so first of all, now I showed you DC-GAN, right? And you saw these faces, right? This is from late 2015. So December 2015, we had these. So, okay, so they look kind of impressive, right? But they look a lot of them just look really outrageous, right? I mean, now that's 2015. This is 2017. Or let's say early 2017. So these are also synthetic. This is, so like GANs were invented in 2014, and since then they've just been spiking in their usage. There's more and more research papers coming out all the time using GANs, and they keep getting better and better at generating realistic looking images. So these are all faces, but they're completely fake, right? But they're looking pretty real, right, aren't they? Like that's a big difference. That's a big difference between 2 years. And actually, so I don't remember if I have this in the slides. So let me show you yeah. So that was early 2017. This is from this past November. So just 6 months ago, November 2017. This is from NVIDIA. How crazy is that? It has, you see hair follicles, like eyebrows, teeth. It's just like outrageous, right? They have a video on YouTube that's an hour long of just this. Just generating faces, right? And I think I have the slide later, so you'll see I did something like as a joke with it. Okay, so a few, like GANs can do all sorts of other things. So, okay, these are GANs that do cross-domain, like sort of like style transfer. It does cross-domain style generation. So, for example, let's say you have a data set of handbags in different patterns, and you have a data set of shoes. You can learn how to do cross-domain generation. So basically, like, okay, handbag of this pattern, turn it into a shoe with the same pattern. Generate a shoe with the pattern of this handbag. Generate a shoe with the pattern of this handbag, right? Or similarly, you could do gender transformation. So these are images of women, and then they've been turned into men. Right? This is a gender transformation, right? And these are men who have been turned into women. I think that's Ben Stiller. Yeah, these are celebrities, I guess. So this is gender transformation. So pretty wild, right? Like, okay, yeah, I do have this. So this is the progressive growing. So you can see how much better they've gotten, right? And as a joke, I downloaded the 1 hour long video that they had, and I trained so you could do face recognition, right? There's a software for trying to recognize the face of somebody. So I trained a face recognition network on celebrity faces. And then as a joke, I went through the one, because these are trained on celebrities, right? These are fake faces, but they're trained on a data set of celebrity faces. And so I thought, wouldn't it be funny to try to find lookalikes, like celebrity lookalikes in their 1 hour long video? So then I ran this face recognition network on top of it, and I tried to find celebrity lookalikes. So this is Chris Rock, and Renee Zellweger. I think the Renee Zellweger especially is like kind of real, right? Kind of convincing. Anyway, that's a joke. Anyway, so there are generative models not just for images but of other things, sounds. So these are point cloud generation. So they're generating like furniture, and you have its own nice like generative, its own latent space to play with. You have natural language generation. So this is a generative model that's basically trained to convert an image into text. It tells a story about an image. So basically, it looks at an image and then it tells a little story about it. So first of all, that's amazing, right? It's like image to text, and it generates an entire like a human came up with it, right? And so like this image, right, is of a beach, and it goes, "We were barely able to catch the breeze at the beach, and it felt as if someone stepped out of my mind. She was in love with him for the first time in months, so she had no intention of escaping. The sun had risen from the ocean, making her feel more alive than normal. She's beautiful, but the truth is that I don't know what to do. The sun was just starting to..." So it just goes on like this, like it's a robot speaking. And the reason why it sounds like that is because it was trained on romance novels. Yeah. Yeah. I think it was trained in romance.
Was it also trained on images?
Yeah. I don't remember the actual. You'd have to look this up. It's called skip dot vectors. Sorry. Is it skip dot vectors? This is from a couple of years ago now. I can't remember. It's made by Jamie Ryan Kiros, and it's, I forget the name. Look up Jamie Ryan Kiros 2015, something like that, and it'll be about this actually. And then Samim, who's a friend of mine in Berlin, if you follow the machine learning space, you probably see him sharing a lot of papers on Twitter. Samim did some funny work with this also, that's online. Okay, so that was image to text. This is text to image. So here you start with a text. You input some text, a red car parked on the side of the road, and then the network generates an image of your caption. So this is from 2016, I think. And then more recently, 2017, StackGAN. So this bird is white, black, and brown in color with a brown beak. and it generates an image that matches the caption. So that's pretty wild, right? Like, you can imagine this is the Photoshop of the future. You just write your comic, book this way. Like, you just generate some captions, and then it generates all the images for you. Right? So it's pretty wild. And it has its own latent space that you can play with. And this is okay. So this makes no sense at all. I think I showed this to you. Did I no, maybe. So now, okay, so that was image. So this is text to image, and we've seen image to text. So what if you take Deep Dream and then run it, and then run one of these image to text generators on it, or a captioning system, right? So this is a joke that I did. Basically, it's just running captioning on side of the Deep Dream video. So the dog has a brown nose. 2 dogs standing on a table. Dogs, dogs, dogs. It's like a lot of dogs. There's a school bus here. I think you'll see that in a second. Wait, I think it's right here. School bus. The bus is yellow. Yeah, it's really wild. Yeah. Or captioning real movies. Like, have you guys ever seen the Boston Dynamics Atlas robots? So I caption these. So it's a bike on the rack, a mirror on the wall, a glass window, man standing in front of a building, person on skis. These are mostly jokes, so. Anyway, okay, so that leads us to Pix to Pix. Are we doing it in time? Okay, we got 15 minutes left. So I'm basically getting to Pix to Pix. We'll see, like, possibly, I think Pix to Pix will be part of tomorrow. So I'm going to introduce Pix to Pix, which is a really, really cool network, and I use it in a lot of really, really cool, like, software, and I use it in a lot of my workshops because it's kind of like a really good Swiss Army knife for a lot of machine learning stuff. I've already shown you a bunch of Pix to Pix projects, I believe. So like on the first day I showed you, we talked about this on the first day if I'm not mistaken, right? So in brief, but I'll remind you, like, Pix to Pix is a generative model. It's a generative adversarial network which is conditioned on an input image. So basically, in short, what it does is it learns an image filter. So you can basically take, for example, a satellite image and convert it into a map, right? So I think I showed this on the first day, right? Or a label map into a facade, or an image of a daytime scene into a nighttime scene, right? And or edges to photographs, right? Like take a sketch of something and turn it into a photograph. And this is actually basically, Pix to Pix is basically like just the combination of the things that we just looked at. It's like a generative adversarial network which is conditioned on an input image, and it learns whatever you give it a data set of. So that's kind of, so it's very, very generalizable, right? So like I use this for this project called Invisible Cities, where I downloaded map tiles. I already showed this, so everyone already saw this, right? So I'll just go through it briefly. Generating map tiles, turning those into satellite images of different cities, right? So you can do city style transfer. Milan in the style of Los Angeles, Milan in the style of Venice. Or just inputting, hand drawings that you make, right? And it learned the relationship between the map tiles and the satellite imagery because I was able to compile a data set of several hundred examples. And that's all it needed, actually. It's trained to work with very few examples. Let me skip that. So like maybe people saw this, like this was anyone see Sketch to Cat? We'll definitely have to. Okay, let's do this. Let's do the demo. It actually does this in JavaScript now, so it downloads the model. So here, I'm going to clear this. I'm going to draw a cat. Here's my cat. So basically, we're going to hit process, and it's going to turn my sketch into a cat. So first it downloads the cat model. So it used to do this on server client, so it would do it on the server side. Now it actually uses TensorFlow.js, I think. And so it downloads the model to the local client, and then my own computer will convert this into an image of a cat. Well, it only has to download the model once, so then after that it'll just have it downloaded in the browser. So running. Here we can give it a third eye. That's gruesome. They have building facades. They have sketch the shoe, handbag, so on. So it's really, really wild. And then someone else did a thing of it, like a portrait generator. Someone did this for Pokemon. So you draw the thing on the right, and then it colors it. And then he like draws an Eiffel Tower instead. And so he gets a Pokemon colored Eiffel Tower. I think that's, yeah. Pokemon colored Eiffel Tower. You can make video with this. So like one of my students did this in Quartz Composer, where he generated the thing on the left, and he ran that through the Sketch to Facade generator. And so he's generating this like morphing architectural facade. Oops, sorry. So this, I mentioned this. This is an artist named Anna Ridler who basically trained it on a film by based on a book by Edgar Allan Poe. Then made a whole bunch of paintings over top of the frames, and then used Pix2Pix to convert the frames into the images, into her paintings, and then she regenerated the whole movie as one of these. So so it looks like this, very abstract. This artist named Jasper van Lonen in the Netherlands, so the Street View API, Google has a Street View API that lets you download Street View images and also the corresponding three-dimensional depth data. So you can get like the depth map. It has all the 3D data. And so he trained Pix2Pix to convert the depth map to the Street View. And so then he would generate his own depth maps and just make like hallucinated, Street View scenes. Generating hands. Right, so this would go on 11. This one's really complicated. So basically, like So this guy, Brandon Dorsey, basically downloaded a speech of Ray Kurzweil, and then he took a bunch of photographs from that speech, and then he would pose in the same position as Ray Kurzweil, making different poses, and then he trained it Pix2Pix to convert the image of Ray Kurzweil into himself. So it's like Ray Kurzweil puppeteering him. So something like that. Mario Klingemann, he would use OpenPose, so we looked at the PoseNet 2 days ago, right? The thing that gets your skeleton, right? So you can take images of people and then extract their skeleton positions and then make a Pix2Pix data set of the skeleton position and the body, and then train it to go from the pose to the body. So he would generate these. He would create a sketch of a pose, and then generate a person's body. This is people reconstructing Connect depth cams. So like imagine if you can take a photograph and get its depth map without actually using a depth camera, right? So maybe in the future you won't need to do the thing that the depth camera does, which is like use infrared light. You can actually just take in a normal input camera stream and get the depth map. You can generate an avatar for yourself. Right? Spider-Man. So then, and I showed this to you, I've also already showed this to you the other day. Mario did this thing with faces where he does the face tracker poses, and then he trained it on 1,500 sketches of faces from a museum collection, and then he would put, take a random set of face points and then generate an image of a face, right? And he did this thing where he reconstructed Françoise Hardy, who's a French pop star from the 1960s. And then basically, let's see if I remember this right. So he took a speech by Donald Trump's press secretary, Kellyanne Conway, in which she famously said alternative facts. Does anyone remember that? It's like the alternative facts thing. Yeah, right? And so this is alternative face. Yeah, it's just you can find this on, look up alternative face. Mario explains it in more detail. And Mario also did the Trump thing, so I just got that from him. Basically, the Trump meat puppet. You guys have already seen this. It's hideous, but of course, it's warning us to a very dark future. So a student of mine did the same thing with Angela Merkel, so the Chancellor of Germany. Memo Acton trained Pix2Pix to convert sketches into paintings, trained on a collection of many museum paintings. Right, and he actually made a real-time application that lets you do this on a good computer, basically. Yeah, this is Pix2Pix HD. And then CycleGAN is the same thing as Pix2Pix, except it has one innovation. It removes the requirement that your data set be paired examples. So for example, let's suppose you wanted to do a Pix2Pix that would convert a horse to a zebra. Well, that would be really hard to do. Can you imagine why? Because Pix2Pix relies on the data set being paired examples. So you'd have a horse in one image, and you'd have a zebra in the second image, which is in exactly the same position as the horse. So that would be really hard to acquire a data set of that kind, right? Because you'd have to get an image of a horse and then the exact same image of a zebra in the same position. So it's really hard to make zebras pose. They do not like to be put into positions by humans. So what CycleGAN does is it lets you just get unpaired examples. You just get a folder of images of horses and a folder of images of zebras, and it can then figure out how to convert a horse into a zebra. Now it's not perfect. It's not perfect. You notice that whenever the zebra passes by the pole becomes striped a little bit. That's because the network does not know where the zebra ends exactly and where the rest of the world begins, and so that leads it to make some really funny mistakes.
Example before, the lines are coherent among the stripes frame to frame because randomly or because they keep tracking the way they
No, it's not. It's actually doing the. So I think in this, okay, so there are approaches that could be taken that would actually try to keep the frames coherent on purpose. I think in this case, the way this was generated was actually just frame by frame. And I think the reason why first of all, it's not really that consistent if you look at it. I think it's shaking around a lot. The reason why it has any consistency is because there is a sort of prior, one type of pattern is more likely than another. And so as long as the two frames are very similar to each other, the pattern will be roughly the same. I don't think they're doing any sort of tracking, but there are approaches that would actually do some sort of a tracking. So one artist named Helena Sarin, whose work I really like, she trained a CycleGAN to convert pictures of fruits and vegetables and stuff into her own paintings. So she just got a data set of fruits and vegetables and data set of her own paintings, and then that's a really bizarre, there's no correspondence between them. Normally CycleGAN is for things like apples and oranges, but it actually learned to generate, a pretty cool aesthetic to it. And so this is some screenshots from that. And then Mario, I think I mentioned roughly how this works, right? So this is I showed this on Monday, right? So Mario's got this thing where he basically has a ping-ponging approach. So he has a model which will convert face tracker data to faces, and the model which goes in the opposite direction, faces to face tracker data. So he just runs it back and forth, and then saves every image of the faces generated. And maybe he does a similar thing that I was doing in the Deep Dream notebook, where I'm distorting the canvas or zooming in or doing this kind of stuff. And if you do that, it just starts to warble around, right? It's kind of this like bizarre looking thing. So yeah, that's a pretty neat approach. And he also did this thing where he trained trained Pix2Pix to predict the next frame in the movie. And then the next frame prediction thing, he just lets it go in a loop, doing a feedback loop, and it just generates like endless fireworks. It's pretty cool stuff. Okay, so that's the end of the slides. So basically, tomorrow what we're going to do is I'm going to take you on a tour of Paperspace, which is a service that I use for, these are just repositories that you can use for if you want to run Pix2Pix and CycleGAN. I'm probably going to do a demonstration of this one tomorrow, and maybe CycleGAN. We'll see if we have time for it. So basically the plan for tomorrow is I'm going to show you Paperspace, which is a cloud computation service that lets you spin up a computer in the cloud, similar to what we were doing with Colab, except it'll be a computer that you have much more control over. You have control over the storage, and you can keep it for a longer time. And basically, Paperspace lets you create clones of computers. So we're going to actually take one of their templates that has all of the software that we need set up already, and we're going to just download a bunch of repositories that are online, open source, and then I'm going to show you how to use them. Now, as I mentioned in the beginning of today, I'm not going to expect you to actually follow, because if all of you are following at the same time, I think like it won't work. Paperspace it'll clog up the internet. And actually, Paperspace is a startup, so they don't have that many computers, so we might actually I've never tried it with this many people anyway. However, the good news is that we're recording this, and the thing that I'm doing is literally going to be from the browser, so you can replicate every step of the way. So you'll have that available to you. So I won't stop you from following along, of course, like if you wish to. Although you need to request access from them to get a GPU instance if you want to have it before tomorrow. So that's something that I would encourage you to just wait until after the workshop. So I think that's about all. Are there any questions about? So tomorrow will be just a big long tutorial, and you don't have to follow along, but it'll be stuff that you'll be able to do directly when you leave this class. So yeah, that's all. So see you tomorrow.